Energy diagrams are basically a visual representation of a chemical reaction showing the enthalpy of the reactants and the enthalpy of the products and how they relate to each other and how we get from point A to point B. They're always going to look a little bit like a peak. The peak is always in the center. The question we need to ask ourselves is, are the reactants have higher enthalpy than the products, or is it the other way around? And how high is that peak and how difficult is it to climb? That will all make sense here in just a moment. So the first thing I want to point out to you guys really quick is we have two reactions on the bottom of your screen. The first one is exothermic. The reason why the first one is exothermic is because notice your energy, which is your y-axis, is going to be, for the reactants, is located right about here. Whereas the products, the energy of the products is way down here. So the trend on this graph is a downward trend, and that's kind of what exothermic means. We're going to be releasing energy to the surroundings. Therefore, the energy within the system is going to decrease as the reaction progresses from left to right. On the bottom, what we have here again is an endothermic reaction, and an endothermic reaction is going to look basically the opposite. Our reactants, our enthalpy of the reactants is right here, and our products is much higher. Therefore, the overall trend in the reaction is a positive trend, which would mean that we are gaining energy from the system. Therefore, this reaction would be considered endothermic. So that's pretty easy to spot. Again, you just look at the heights of the reactants and the products and see if they're going up, that is endothermic. If they're going down, that is exothermic. Okay, pretty straightforward. The next thing I want to point out to you guys is there's something here called the delta H. So the delta H, shown here in green, is the overall change in enthalpy. Remember, guys, that the delta means change. Capital H is enthalpy. So that is the change in enthalpy. If I could spell that correctly, let's try that again. That was not well done. Enthalpy, there we go. So the overall change in enthalpy. So the dotted line here represents, on our top reaction, represents the starting point of the reactants. Here is the ending point of the products, and that change from there to there is the delta H, the change in enthalpy. Now for this particular enthalpy, for this top reaction, it would actually be a negative number because again, we're changing from a higher to lower, therefore that would be a negative pattern. On the bottom reaction here, again, we have our reactants shown by the dotted line here. We have our products, which end up right about there. And again, our delta H is going to be the change from the beginning to the very end. And its delta H, or enthalpy, would be a positive value because again, we're going in an upward pattern, which of course is endothermic. So this one here would be a positive delta H. This one here would be a negative delta H because the change is losing. The bottom one, the change is gaining energy. Again, just to repeat, where are we gaining it from? Of course, the system, right? All right, the next thing I want to point out to you guys is something called activation energy. Activation energy, like it says here, is the energy required to start a reaction. The example I often use is like a simple match. I can put a match on the table, and I have no concern that that match will flare up and catch fire all by itself. Why I know that is because there's no energy being put into the match in order for that reaction, which we call fire, to begin. The way we get a match to light is we have to strike it against a sandpaper or some sort of coarse substance, which would increase the friction. That would be heat energy, and that heat energy would overcome the obstacle, if you will, the requirement of the input of energy in order for that match to catch fire. To use proper chemistry terminology, that would again would be the activation energy. Now, the way we show that is it's a capital E with a subscript lowercase a. You guys know from Einstein's famous E equals mc squared that capital E means energy. It always does. So E with a little subscript a technically means the energy of activation, but we often just say activation energy because I guess it's a little easier. Anyway, on the graph here, what you guys see in this red portion right here is the hill which you have to climb in order to get to the top. So the change from the very beginning, which is the reactants from here up to this line, like it shows right here, is the activation energy. That is the uphill portion, which must be overcome. in order for that reaction to start. Another very common and easy example I could explain would be like a roller coaster. In a roller coaster, there is one time where they put energy into the system, and that would be when you first sit in your chair and you begin, right? The first thing that every single roller coaster does is your cars get pulled up the hill. It has to, there's an input of energy, it goes a chugga, chugga, chugga all the way up the hill. Once you get to the very top of the peak of the roller coaster, from there on out, it's all an output of energy, and it's all just gravity and momentum and inertia, right? It's the exact same thing with a chemical reaction. We have to pull or push the cars up the hill. That requires energy. Once we get to the top, we all throw our arms up and we all start screaming and we have fun all the way down to the bottom, right? Exact same thing, like I said, in a chemical reaction. So that uphill portion, again, is called the activation energy. It is from the beginning, wherever that may be, from the beginning to the peak. The end has nothing to do with it because remember, this is all inertia and gravity, at least on roller coaster, right? Well, it's the same thing with the reaction on the bottom. It's from the very beginning where you get into the car and you get pulled up the hill, and it's the uphill portion all the way there, up to here. Again, the products have nothing to do with the activation energy because again, this is all downhill and there is no energy being put in, there is energy being released. So activation energy, again, just to rephrase, is the energy required for a reaction to start. It's what must be put into the system. Once that threshold is reached, the reaction will progress all on its own, right? Okay, now that we understand that, let's go ahead and move on to the next part. So that is true for one direction. There's also something called a reverse reaction. Now a reverse reaction, wow, I misspelled that. See, this is why you don't type or write and talk. Not as easy as it looks. The reverse reaction begins with the products as the reactants and the products and the reactants of the products. Okay, that sounds really confusing. What they basically mean is instead of going from right to left, we're now going to go in the opposite direction from right to left. So in this case, if we're going in the reverse reaction, these are no longer the products, these are the reactants, right? And again, these are no longer the reactants, these become the products. Okay, the exact same reaction, but going in the opposite direction. So the activation energy over here was very tough, very hard to overcome, but in the reverse reaction, the activation energy is actually going to be much, much smaller. It's going to be from here to here. That would be the activation energy in the reverse reaction. This is for the forward reaction. This is for the reverse reaction. So you see how that works, right? Also, notice one thing else is that our delta H would also change. Our delta H let me go ahead and get that out of the way so you guys can see it. Our delta H in the forward reaction, which is this way, in this direction, our delta H again is positive, right? Because again, we're going in this direction. Well, if we're now going in the reverse reaction from right to left, then we're going in this way. So that now becomes a negative delta H. So you need to be able to understand that if we reverse the reaction, we also switch the delta H from negative to positive or positive to negative, whatever that may be. Because again, we're going from endothermic to exothermic or vice versa. The next thing it says, if the forward reaction is exothermic, then if you're going the other way, going backwards, it would then become endothermic. See how it switches. Likewise, if the forward reaction is endothermic, then if you go backwards, it becomes exothermic. And again, don't forget to switch the sign of the delta H. Again, you guys already know that from Hess's law. In this particular reaction, again, when we are breaking bonds, what we tend to do is lose energy. We release energy when you break bonds, but when you form bonds going to the left, hydrogen plus oxygen making water, we actually gain electricity, what am I talking about? Energy. So that's how that works. Again, just notice that the delta H changes, that's all. All right, the next thing I want to talk about real quickly is a catalyst and the influence of a catalyst has on a reaction. A catalyst, like it says right here, is something that's going to lower the activation energy. So if I have my reaction here, my endothermic reaction at the top of the screen, my activation energy is from all the way down here, all the way up there. Now that is a very difficult thing to overcome. But if we add a catalyst, what it's effectively going to do is it's going to make the curve not have to go as high. Notice my starting point is not affected. My ending point is not affected. The presence of a catalyst does not change the starting point or ending point because it doesn't change the reactant to the products. It doesn't do different chemistry. All it does is it makes that peak, that very difficult energetic peak, it makes it lower, therefore it's more likely to occur. If the peak is not as high, well, then it's easier to get over, and therefore it requires less energy to overcome, and therefore the reaction is more likely to occur. It doesn't make the reaction faster, it does not speed up the reaction, but it makes the reaction much more likely to occur. It lowers that peak. The last thing I want to point out real quick is this peak is actually called the activated complex. The reason why we call it activated complex, which I know is kind of a funny term, is because if this is the starting point here, the reactants, and this is this ending point, which is the products, then the activated complex is something kind of in between. It's not really a reactant. It's not quite a product yet either. So we call it a complex, something kind of in between. And it's activated because, again, the activation energy has been put in. So the reaction is started, but it is not finished. Again, on the roller coaster, that would be when you're at the very top of the highest peak. You know you're about to go down the other side of that really fast, but you are not at the finish line yet, and you're definitely not at the starting point. You are somewhere in between. So that peak, this peak right here, is the activated complex. That's just one more terminology you need to be aware of. All right, so let's go ahead and try these questions based on this graph we have at the top of the screen. So the very first question, number 1, says, what is the heat content? Notice again, that's your y-axis, in kilojoules. Kilojoules, again, is just 1,000 joules, and joules is a unit of energy, heat energy specifically. It says the heat content of the reactants of the forward reaction. So again, forward reaction, of course, means we're going from left to right. So the heat content of the reactants are right here. So that would be this number there, which is 80 kilojoules, okay? Number 2, what is the heat content of the products of the forward reaction? The products, again, you know, are over here at the ending point. The products are 160 kilojoules, okay? 160 kilojoules, as you guys can see right there. Okay, next thing, number 3, the heat content of the activated complex of the forward reaction. Remember, this right here is the activated complex. So if I draw a line across the peak, it's 240 kilojoules. That is the activated complex. Again, the highest point on the peak. All right, number 4, it says the activation energy of the forward reaction is how many kilojoules? So activation energy, remember, is from the very beginning to the very top. It is from there to there. That is the activation energy, or E with a subscript A. So 240 minus 80 gives me what? 160 kilojoules. 160 kilojoules. Again, that is from the very beginning down here to the very top, the amount of energy that must be put into the system for the reaction to progress. All right, so then number 5, it says the heat of reaction, or the delta H of the forward reaction. So the delta H is a comparison of where you start to where you finish. This has nothing to do with it. From the start, which is 80, to the very finish, which is 160. So 160 minus 80 gives you 80 kilojoules. So again, that is 80 kilojoules. Now again, we're going in this pattern. So is that a positive 80 or a negative 80? That would be a positive 80 kilojoules because we're going from 80 up to 160. So we have gained 80 kilojoules of energy. So that again would be a positive 80. Let me go ahead and try to do that a little bit nicer. Okay, so then that means, let's go for number 6. The forward reaction is endo or exothermic. Again, like I just said, is going an upwards trend. Therefore, that would be endothermic. We are gaining energy. All right, so if that's all the case, then let's try the next one. So number 7, it says the heat content of the reactants of the reverse reaction. So now we're going this direction. So we need to kind of think about these differently. These are now the reactants, and now these are the products. It's the exact same reaction, we're just switched the direction of it. So therefore, the heat content of the reactants in the reverse direction is here, and that is 160. Okay. Number, what is it, 8? The heat content of the products of the reverse reaction, there's the products, it's about 80 kilojoules. Okay. Number 9, the heat content of the activated complex. Again, the activated complex is right here. It is still 240. That has not changed. It's not surprising that these two have not changed because it doesn't matter if you're going left to right or right to left, the peak is the peak and the peak does not change. So the activated complex will still be the same number. Number 10, the activation energy of the reverse reaction. So before in the forward direction, we had to climb that very difficult hill, but going in the reverse direction, we only have to go up this smaller hill. So our delta H would be a change from the beginning, because remember, we're going from right to left. So from the beginning is right here at 160, and then the peak is right here at 240. Therefore, our activation energy is just this right here. Our E subscript A is going to be 240, which is the peak, minus 160, which is the reactants, gives me 80 kilojoules. Sorry, guys, a lot of these answers turn out to be 80, which I know is a little confusing, but I'm hoping you're following my logic because I'm explaining as I go. It is unfortunate that the numbers do repeat so frequently. I do apologize for that. Number 11, it says the heat of reaction, or delta H, the change in enthalpy of the reverse reaction. So remember, the delta H is a change from the beginning to the very end. This has nothing to do with the delta H. It is from the beginning to the end. This is your delta H. So it's going to be 160 minus 80. That would give me 80. Would that be a positive 80 or a negative 80? Because again, we're going in this direction. It would be a negative 80 kilojoules. Now again, notice that these two are the same number because your delta H will not change no matter which direction you go. Notice the only thing that changed is on number 5, the delta H was a positive value, and on number 11, the delta H is a negative value because we're going in the opposite direction. The number is not affected, but the sign is switched. If it was positive, it becomes negative, or vice versa. You get the idea. All right, so then number 12, it says the reverse reaction from right to left. Is it endo or exothermic? Remember, it's going in this way, so we are losing energy, which of course will be the opposite of the forward reaction. Finally, it says we're going to draw a dotted line in order to show the how a catalyst would affect the reaction. So let me go ahead and do that. Let me go and change my colors just so I can see a little bit better. So if I added a catalyst, then it's going to look something like this. It doesn't really matter if we're going from right to left or left to right. Remember that your reactants is unaffected for the products in the reverse reaction, and your products or the reactants in the opposite direction are unaffected. Again, the only thing that has changed is your activation energy. So for the activation energy with the catalyst would be this, and the activation energy without the catalyst would be this. Notice that's a pretty big change, right? So that's what a catalyst does, is it brings that peak lower, lowering the amount of energy that is required to start the reaction, therefore making the reaction more likely to occur. All right, well, that is it, guys. Again, as always, thank you very much for watching, and please let me know if you have any questions. Thanks, guys.